All right, so as part of this video, then we are going to implement the read function related to operations on the proc entry that we had added in the previous video. But the thing is, in the previous video, I screwed up my kernel, landed in a crash state, so I had to restart. And so what I have done is I have stopped my primary instance, and I'm going to just go ahead and restart it again. And once it restarts, I have VS Code here in the background that I'll again kind of connect to the primary machine and then get inside. So let's wait for this to come up, and let's in the meantime discuss what we are going to implement. So let me go here again. This is the proc_fs.h. This is the file system or the header file that we are interested in, and within that line number 29, which talks about the structure proc_ops. And in this function we are wanting to implement a function of this nature. So this here is a function pointer, and the variable that will be pointing to the function pointer is the proc_read, right? And so let me just copy this because the signature is important for us. And the multipass has started the primary machine. Yes, it's running. So I'll go to VS Code, then go to Remote Explorer, then go to the IP address, and within that LDT, click on this arrow, and it should attempt to connect. I'll enter my password, and it's connected. Perfect. So this was the code that we wrote last time, and one of the things that I copied now was this, right? So I want to implement a function now which is of this type, right? And I'm going to call it, and let me just cheat here, and I'm going to call it, pajama read, right? And then it is going to have function parameters of this nature, right? And so this, let's say it's going to return 0 because that's success. And much like, the case here, I'm going to put a print statement here, and then put this here. We don't want entry or exit, so this is what we print. Now again, notice that this name here is different than what it is here, but all the other parameters here are essentially same. And I would want to, like, here there are no names to the parameter, which is fine, but I'm wanting to give these guys name. And let me also kind of copy over the names here, just so that our function parameters have a name. And let me also kind of align this right here, and let's put it right here this way. We don't need this anymore, so I'm going to get rid of this. And the other thing I'm supposed to do is, so remember, one of the entries here, and that's what we kind of copied, one of the entries within this struct is the proc_read. This is a variable as seen or as available within the struct proc_ops, and this variable happens to be a function pointer. So I'm going to take this variable, right, and say, hey, to this variable I want to assign value of whatever the address of this function is. So that's how we are going to populate it. And let me just go ahead and quickly check if I'm committing a crime here accidentally, because I don't want this to fail. Yeah, this is correct. And well, the thing I was looking up on the side is whether or not there should be a comma here. It's not required. Comma or a semicolon, right? That's not required. All right, perfect. So we have our function here, which is supposed to be kind of called when the read on that proc file, a proc/pajama_driver is called, right? That is what we're trying to do. And then as we are initializing our module here, we are saying, hey, please register the driver_proc_ops structure as the structure holding the function pointers that are supposed to be called when the procs file entries read or written to, and we can visualize this. So again, we have the proc entry here, which is the 𝘁𝗓𝗓 driver. This we achieved in the last video, and now what we are doing is, through this we were binding actions on this: read, write, open, close, all of those actions. We were binding what this structure here. We were saying that this structure is going to have function pointer to various actions, right? And this function pointer then goes back to this function. So every time we call a read on this function will get called, right? The kernel will understand that this driver has this function which needs to be called every time someone tries to read this particular virtual file. So that is why we are writing or doing all of this, right? And again, once you see the demo, things become clear. What I'm going to do is also make this static. And the reason behind making this static is I want this function to be only available within this file. We don't use it outside of this file. All right, perfect. And now what I'm going to do is, okay, uh, let me close this. The way you open a terminal is go to the main menu and create new terminal, right? And I'm going to drag it on the side. So I'll go ahead and do make clean, just because we want to build fresh. And then let me hide the sidebar. All right. So let's go ahead and try to do make. Yeah, things have compiled correctly. Let's do ls-mod to ensure yes, the driver is not loaded. Obviously, let's check on sudo dmessage. A lot of kernel logs here. We'll clear those, right? So that is gone now. And let's also do ls/proc, and there is no 𝘁𝗓𝗓 driver here. Yep, not there. All right. Now we'll do sudo insmod ldd.ko. Thing seems to have gone all right. We'll do ls-mod first. Yes, our driver exists here. And then also go ahead and kind of do dmessage. Very nice. So, entry and exit was called. So entry and exit was called. Everything is great so far. Now we are going to check whether, the proc system has our driver's virtual, file entry, and it does. So that is also good. Now we are going to attempt to read this, and let's see what happens. And before that, this is the D message, and we are going to do cat. So cat is a program that tries and reads the given file. So 𝘁𝗓𝗓 driver, okay, nothing got printed, which is fine, but at least it exited without errors. So in the last video, it had exited without, sorry, with errors, and the error was input output error, something like that, right? And we are going to do sudo dmessage and notice that 𝘁𝗓𝗓 read, which is same as this was called. So what we have succeeded so far in doing is, and this is like absolutely crucial, this was our virtual file system. We added an entry, by the name 𝘁𝗓𝗓 driver here. And then when we loaded the LDD in the init, we created this entry. That was number one. But the second thing we did while we were creating this entry, we said, hey, there is this, there is this struct which is of the type proc ops, and within that, the proc read variable that we are assigning to a function, and that is the function you call when a read operation is performed on this file. And what we saw right now was that we provided a function pointer here, and that function did get called when we attempted a read on this file. And now this is, absolutely crucial and very fundamental to how drivers or how the user programs interact with the drivers. The the driver is associated mapped onto a file. The interactions of the driver are mapped onto a file, and interacting with the files from the user space essentially triggers some associated functions in the driver. This is absolutely key. And recall that at some point I was telling the pieces of C, that you would need to know is, structs and then function pointers. Those two things are enough, an absolute mandatory thing actually. Okay, perfect. So one thing that we haven't answered, right, which you would have seen, is who is passing all of this, right? Why these input parameters and who is passing these? So the answer to this is, when the kernel is like hunting down our driver and then calling this associated operations, file operations related functions, the kernel is going to provide, all these information. The kernel is going to provide them. And now in the next one, what we are going to do is we are going to see if when we perform the cat operation here, can we print something in the user space, right? And again, let me make this very clear. So when we perform the read here, the read was happening from the user space. So cat slash proc slash, pajama driver. This was being read from the user space. The read on this was passed to the kernel, and this is like then the kernel space, right? This right here translated into a system call, right? And syscall of what type? Read type. So the kernel caught it. The kernel figured LDD is the driver for this, and then LDD had the proc. And okay, just give me a moment. Let me clear this. Yeah, so we had the proc underscore read here, right, which was this. And so the LDD driver just called this. And then we had the print k. And the print k prints into the kernel buffer. So that is where we see this line, that within the kernel buffer, we do see that the read operation was called, executed. What we want to do is print a message, send something from this back to the user space. And this we haven't achieved. And once we achieve that, what we would have seen is that the driver can pass some information back to the user. And why is this important? Okay, let me let me paint a picture, right? So the reason this is important is, let's say you have a camera, right, which has taken like a picture of you here, right? And so the camera somewhere is connected to your Linux machine, right? Let's say this is the Linux kernel. And so there is like, some CD, the camera driver. And so what's going to happen is there is some, buffer here or some memory in the camera itself. And your, snapshot is right there. And so the driver, and let's say we have the camera app here, right? The app. And here you click, like you click on the shutter button and kind of, you want to take a picture. So what happens is that action is translated to some system call for the driver. The driver then goes and reads the image here, brings it back, and then it's supposed to pass it back to you. And in fact, the cameras also stream that picture continuously, so they are essentially passing information back to the user space, right? And that I'm saying we haven't achieved right now. We haven't kind of copied content from user space to kernel space, and we haven't copied from kernel space back to the user space. And this copy happens because you don't want them to share the common you definitely don't want the user application to be able to access the kernel's memory space, any memory space that is required or managed by the kernel. Because then what will happen is the application has a hook inside, or like a way to get into the kernel's memory, and then malicious actors can actually write some code that can hijack your kernel, and we don't want that. So what is better is we provide mechanisms wherein the kernel can copy data from user space into its own space, operate on that, and then send it back to the user space. So what we are now wanting to explore is, can we send back some data from the kernel space to the user space?